During the 3 years of my PhD, I have studied several issues that affect modern and future network. The main issues in which I worked are the analysis of high-speed network traffic, the security issues related to node mobility, how to mitigate massive attacks generated by self-propagating malware such as internet worms, and issues related to Byzantine fault tolerance in systems and services. Now, I will not have the time to go into detail in each of these research activities, but I will spend most of the time focusing on the first of these areas, that is analysis of high-speed internet traffic, while I will just present a short list of main contributions in the other field. So first of all, in order to analyze network traffic, we use network intrusion detection systems. A network intrusion detection system is an appliance that analyzes all the network packets that are flowing through a monitored link in order to detect illicit activities such as network attacks or network intrusions. Network intrusion detection systems work at runtime, meaning that they have to analyze all the network packets while they are flowing on the monitored link, so that each packet is gathered at wire speed. That of course introduces a problem, because if the computational capacity of the internet traffic analyzer is not enough to keep up with the flow of packets that it is supposed to monitor, then there is packet loss, meaning that some of those packets are not analyzed, they're just discarded, and if the network attack is included in those packets, then it cannot be detected. This problem is also exacerbated by statefulness analysis, meaning that each network intrusion detection system doesn't analyze network packets individually, but it performs a stateful analysis in which connection tracking and reassembling is involved. This kind of analysis approach is definitely more difficult to evade from an attacker point of view. However, the need to reassemble and track each concurrent connection introduces high computational costs, and high computational power is needed in order to analyze network traffic. This is basically the reason because traditional network intrusion detection systems have several problems in dealing with high-speed traffic. In this chart, you just have an example of the performance of a common network intrusion detection system built on custom hardware, in this case an Intel Xeon 2.4 GHz. On the y-axis, you can see the rate at which the network intrusion detection system is losing packets. On the x-axis, you can see the generated bandwidth, that is the traffic throughput that the sensor is supposed to analyze. As we can see from the red line, our network intrusion detection system is able to monitor all the packets without any packet loss for bandwidth lower than 40 megabit per second, while it starts losing packets for bandwidth higher than 40 megabit per second. This result means that even a fast Ethernet can be enough to saturate the computational capabilities of a network intrusion detection system. The solution to this problem that we proposed is a parallel architecture for network intrusion detection system that is appealing because it allows to distribute the load related to traffic analysis among a set of parallel network intrusion detection systems working on different subsets of the traffic that we are analyzing. For example, in this picture, we are analyzing the traffic flowing on a network link that connects an internal network to an external network, and that is too high to be analyzed by a single network intrusion detection system. Now, I will not go into detail in the functions of each of these elements. The first layers of the architecture have the purpose of distribute the network traffic across the set of parallel network traffic analyzers. So we have network intrusion detection systems working on different traffic slices. Their alerts are collected by a single alert aggregator that serves to the network administrator in order to have a single interface, which is functionally similar to the interface used to manage a single network intrusion detection system. The most intelligent component of the architecture is the coordinator, whose goal is to coordinate all the load balancing activities involved in this architecture, thus to maintain the load balanced among the parallel network intrusion detection system. This is an important problem, an important issue for all the parallel architectures for network intrusion detection system. Indeed, network internet traffic is known to be highly variable and characterized by long-tail distributions and high traffic bursts. So dynamic load balancing is needed in order to keep the load balanced among the parallel network intrusion detection system and avoid overload and packet loss in one of those sensors. However, as we said before, we require network intrusion detection systems to perform stateful analysis, and stateful analysis requires all the packets belonging to the same connection to be tracked and reassembled. This opens an issue, because when I dynamically balance the load among parallel network intrusion detection system, I am basically moving open connections from one intrusion detection system to another, so that the destination network intrusion detection system is forced to analyze a connection that is already open and that is picked in midstream. So it hasn't the necessary state information to perform stateful analysis. It falls back to simplest stateless analysis that can be very easily evaded by an attacker. To solve this issue, we devised and designed a new cooperation strategies for network intrusion detection systems. In that cooperation strategies, we allow parallel network intrusion detection system to cooperate by exchange their internal state information, so that each intrusion detection system is able to build its partial state information based on the partial subset of traffic that he is analyzing, and then to exchange its partial state information with the state information generated by other network intrusion detection systems. So to merge those state representation and build a complete state representation that can be used for stateful traffic analysis. Of course, in order to implement that, we have to address some challenges. The most important of them are the implementation of a new sensor communication scheme, and of course of all the mechanisms and algorithms that are related to partial state management. We also have some requirements that we have to meet in order for our proposal to be really useful in the field of network intrusion detection. And the first one is to provide state migration facilities with low delays, because of course we want to perform runtime analysis, not batch analysis. And the other one is to have unmodified detection rate, meaning that migrating and merging the state have to guarantee the same performance of a single stateful network intrusion detection system. This is just an outline of the main components of the state migration framework that I have designed. In the lowest layer, we have the network intrusion detection system detection engines, which are basically the software module that perform the actual analysis of traffic. Each detection engine is able to build and maintain its partial state information. On top of those layers, we built a new layer that is responsible for state migration management. In particular, this layer is able to access the internal data structures of each detection engine to retrieve the state information and to transform those state information in an opaque and independent representation that can be transmitted over the network. The network transmission is handled by the network communication layer that is on top of that. This framework has not only been designed but also implemented. I will not have time to go into the implementation details. However, this is a patch against Snort, which is a popular and widespread open source network intrusion detection system. We are working on the state of the Stream 4 detection engine, which is the detection engine that is responsible for creating and managing the state of all TCP connection and UDP traffic flows. Now, this graph represents the delays that are introduced with state migration. As I said before, one of the requirements was to operate state migration with low delays. On the y-axis, we have the time required for state migration to happen, and on the x-axis, the analyzed traffic throughput. The red squares represent the time that is required only for state export. That is, the time required for the state migration management layer to access the internal data structure and create the external state representation. As you can see, this time is very low. It's basically 2 milliseconds in most of the cases. On the other hand, the blue crosses represent the time needed to perform a complete state migration. That doesn't involve only state extraction, but also the transmission of those extracted state information to another network intrusion detection system. As you can see, the time is dominated by network latencies. And however, this is not an issue for a network intrusion detection system, because delays of less than 1 second are definitely tolerable. Now that we have that new state migration mechanism, we use it to design and implement a new load balancing mechanism that allows for the first time to implement dynamic load balancing together with stateful pattern matching. The main idea is to extract the internal state information and make the state information follow the traffic that I dynamically reassign during load balancing. so that the destination network intrusion detection system will not only receive an already open connection, but also the state related to this connection that has been created by the network intrusion detection system that was analyzing the connection before. We implemented that new stateful and dynamic load balancing algorithm. In this chart, we can see an example of the first version of this algorithm in which load balancing and load state was measured only by load samples without any statistical aggregation function taken on load samples. On the y-axis, we can see the bandwidth that is basically directly proportional to the load of the parallel sensors in the parallel architectures. The three lines of different colors represent the load experienced by three different parallel network intrusion detection systems. As we can see, at the beginning of the experiment, at time t equals 0, there is a severe load imbalance because all the load is on one sensor while the other are completely unloaded. The network intrusion, the dynamic load balancing algorithm triggers and start to distribute evenly the load among the sensors. Now, this is definitely an improvement with respect to the non-balanced situation. However, we can see that there is space for improvement, and we improve this algorithm by using statistic-based activation triggers. This is the same experimental setup in which at the beginning of the experiment all the load is on a single sensor while the other are completely unloaded. As we can see, however, with this improved dynamic load balancing algorithm, the load is more evenly balanced among the sensors. This, thanks to the good performance of this algorithm, we are able to achieve an important result that is good scalability of the overall ParNID architecture. Indeed, on the y-axis we can see the traffic that the ParNID architecture in its whole complex is able to analyze without losing any packets, and on the x-axis the number of sensors. As we can see, the highest manageable load grows almost linearly, is able to scale almost linearly with the number of sensors used in the proposed architecture. Now that concludes my presentation on the area of high-speed network traffic monitoring. The next area that I will go to analyze, to take into consideration, is node mobility, in particular security issues related to node mobility. Node mobility in IP networks can be achieved by the use of the mobile IP protocol that provides transparent routing of IP packets to mobile nodes, even if they are not connected to their home networks, so while they are roaming. However, mobile IP introduces a couple of security issues. At least, mobility introduces several security issues. We addressed and studied in detail two of them. First of all is that node mobility prevents stateful analysis. This is because when a node roams from a network to another, the network intrusion detection system installed in the new network doesn't know anything about the state of the connection that the mobile node had already opened. So it is not able to perform a stateful analysis, and it has to fall back to stateless analysis that is open to network intrusion evasion. This is the reason because node mobility is open to stealth attack, and by stealth I mean that a mobile attacker can leverage node mobility in order to perform attacks that are not detectable even by well-configured, state-of-the-art network intrusion detection systems. The other issue is well known, and it's the incompatibility between triangular routing, that is the default mobile IP routing scheme, and egress filtering, which is a best practice in the configuration of packet filters, for example, firewalls and routers across the internet. So if a network wants to deploy mobile IP, it has to relax its security policies. Our main contribution in this area are the identification of new mobility-related attacks, so new attack strategies that mobile nodes can leverage in order to evade detection, and also solutions to these issues that are based on NIDS cooperation scheme. In this context, we use our state migration mechanism in order to make the network intrusion detection system deployed in the network involved in the node roaming to exchange their internal state, so that the state follows a mobile node while it roams through different network, allowing the network intrusion detection system to perform, for the first time, stateful analysis. Moreover, we developed secure triangular routing, which is a novel routing scheme for mobile IP that is able to solve the incompatibility between triangular routing and egress filtering, so that we can achieve the same performance of triangular routing without the need for security policy relaxations. I'm sorry. Okay. The next area which I am describing is our research in the field of massive attacks generated by self-propagating malware, such as internet worms. Internet worms and self-propagating malware in general is usually organized in botnets, meaning that there are networks of up to hundreds of thousands of compromised machines that operate on a common goal. For example, they are the basic infrastructure that attackers use to launch distributed denial of service attack and also to send spam emails. A botnet usually propagates by exploiting widespread software vulnerabilities. Infected machines randomly generate new targets and attack those targets with widespread vulnerabilities, which means that, as a consequence, geographically distributed networks and hosts are targeted by the same attacks. In this area, our main contribution is the design of two new architectures, one based on a hierarchical design and one based on a decentralized peer-to-peer design, whose main goal is to provide cooperation, so the ability of network interaction systems deployed in different networks to cooperate. By cooperation, we mean that we create an infrastructure that is able to guarantee high efficiency in analysis, because the same attacks the same malware, for example, that have been detected in different distributed networks are analyzed only once, and not once per each network. And what is more important is that we use those architectures in order to provide yearly dissemination of the result analysis to all the participating network. This is the most important contribution, because a participating network can receive the result of the analysis of a malware when this malware have only targeted other networks, so that that network has not yet been attacked and have time to deploy proactive countermeasures. Those features are common to both the hierarchical and peer-to-peer architectures. The peer-to-peer architecture, that is an evolution of the hierarchical design, also introduces new interesting features such as higher scalability, self-adaptation, and increased dependability, because there is no single point of failure in the peer-to-peer infrastructure. The last area in which I focused my research is related to Byzantine fault tolerance, in particular to systems and services that are able to tolerate Byzantine faults and Byzantine users. This research has been carried out in strict collaboration with the Department of Computer Science in the University of Texas at Austin, in which I've been visiting for 8 months last year. On this field, we have two main contributions. The first one is the design and implementation of Aardvark, which is a new Byzantine fault tolerant protocol, whose main contribution is the ability to provide high throughput of thousands of operations per second, even under attack or under Byzantine faults. The second one is FlightPath, that is a BFT cooperative service, and it is able not only to provide good performance, but also it relies on a gossip protocol that is probably secure. I will not go into detail on that. Of course, further details can be obtained from the related publications. So to conclude, the main contribution during my 3 years of research during my PhD are, first of all, a new state migration mechanism that can be used to enable cooperation among different stateful network interaction systems. This state migration framework has been used within the ParNIDS architecture, that is the first parallel architecture for network interaction systems, supporting both dynamic load balancing and stateful analysis of dynamic load balanced traffic. On the area of node mobility, we identified a new set of attacks that relies on node mobility, so new techniques that can be used by mobile attackers in order to evade detection. We also solved these issues by designing a new NIDS cooperation scheme that allows distributed NIDS to cooperate and stateful analyze mobile connections. We also developed the secure triangular routing, which is a new routing scheme for mobile IP that overcomes the incompatibility between triangular routing and egress filtering. We designed and implemented two new architectures for cooperative malware detection and analysis, able to provide the cooperating networks with early detection and early analysis results. And we designed two new BFT protocols and systems. one point I want to stress is that all the research activities that are presented in these slides have been not only designed but also implemented in prototypes that have been used for real testing. Those are a list of my publication, and that concludes my presentation. Thank you for your attention. Hope you've enjoyed.